Hi Trig, here's the last part of the notes for today. This is the second time I'm recording it. The first time it was too long, so they cut it off. But I have a little pulley system going here. Obviously there's some rotational motion here. There's some things going through radians and degrees and inches per second or whatever we're talking about. So just take a look at this and observe for a second. If I asked you the question, which one of these is moving faster, how would you answer? Think about it for a second. Okay. If your answer was in the form of a question, well, wait a second, how fast is it moving? Which one is moving faster? Depends on what type of speed we're talking about. Okay, if we're talking about linear speed, that is how fast these things are moving on the outside, then they would be moving the same. That red dot is showing you that because they're connected by this belt, they're always moving at the same speed. However fast this one's moving on the outside, that's how fast the belt is moving. However fast the belt is moving, that's how fast this one's moving on the outside. So their linear speeds would actually be the same. Now, looking at the two little dots, how fast these two dots are going around compared to how fast these two dots are going around, you would say, well, it looks like the little one's going faster. And it is, angularly. Okay, its angular velocity is faster than the big one. The number of radians it goes through in a second, or the number of degrees it goes through in a second, or however many revolutions it can do in a minute would be greater, okay? Because it's smaller, so it's having to go around faster to get to that same speed that this one's going at. So we had two ideas today on these notes. One of the ideas was me and my daughter on a carousel. In that instance, we share the same center. The center of our circles is at the same spot. We would have the same angular speed because every time I go around once, she goes around once. Okay, this one, the second one, because these are connected by a belt, they would have the same linear speed, the outsides, feet per second, meters per hour, whatever the case may be. So with those two ideas, we can kind of merge them and we get some different problems that we can work through. One of them being the bicycle problem on the partner one, whoever had that. Tough one. Come see me on office hours if you need help with that. Okay, so let's finish these notes up. We'll do one example problem. Looks something like this. I have a little machine being pulled here by a pulley system. Wheel number 1 is driving wheel number 2. They're connected with a belt. I have the radius of both. I know that radius or wheel number 1 is running at 30,000 revolutions per minute. That's what RPM stand for. I'm asking you, what is the linear speed in inches per second of wheel 2? Well, based on what we just said and what we just saw, their linear speeds are exactly the same. So whatever the linear speed is of 1, that's going to be the linear speed of the belt, which is exactly the same as the linear speed of 2. So when I say find the linear speed of 2, we're actually finding the linear speed of 1. Okay, and now we can just turn this into a dimensional analysis problem like we were doing. We have units we're trying to convert back and forth between. So I'm talking about finding the linear speed of 1. Well, I know 1 is going out at 30,000 revolutions every 1 minute. Okay, I know I'm trying to get it into inches per second given to me in the problem. So there's my little river I'm trying to get across. Let's handle time first. In 1 minute, there are 60 seconds. Minutes are canceling. Now I'm left in revolutions per second. I want inches per second. I don't want revolutions. So I know whatever conversion factor I'm going to use here, I need to have revolutions in the bottom. Okay, so now the conversion factor, 1 revolution. 1 revolution is 1 circumference. That means 1 time around. 1 time around, the circumference of a circle is 2 pi r. That's the formula for circumference. Okay, now remember, we're talking about wheel number 1. So this r value we want to use is actually the r value of wheel 1. So 8 inches. There are 2 pi 8. There's 16 pi inches in 1 revolution for wheel number 1. Revolutions cancel. I'm left in inches per second. The last step is just to multiply everything on top, divide by everything on bottom. We're dancing. That's it. Okay. Still a pretty big number. 25,133 inches per second. And without further ado, sorry for the delay, Group A people. We had a little technology malfunction. We'll deal with it. We'll ride through it. Page 370, 83, 85, 87. And then 89 through 92 and 95, all word problems, all dealing with circular motion of some sort, of one sort or another. Do your best with them. I'm going to set up some office hours tomorrow morning. If you feel like you need to come to a Zoom, meet with me, and I'll go over some things, we can take care of that. But I will see you on the flip.